In the last lecture, we talked about the use of climate models to predict how climate will change in the future. But in order to trust the climate models' ability to predict the future, we need to know how well do they predict the present climate. So, this has been the goal of the Climate Model Intercomparison Project, CMIP, and in this project large number of groups who have climate models, they run the same scenario for present climate and future climate, and then we compare all these models to see how well do they agree with each other and how much do they differ. Okay. From these comparisons, we get an idea about how good or how bad the models are. Now, the first example I discussed, and which I will repeat because it is important, the major problems that the coupled models have is what is called the SST bias. That is, the temperature of the ocean is lesser than what is observed. You can see two versions of the CMIP series. CMIP 3 is the old one, CMIP 5 is the more recent one, and average over 50 years you see that there is a huge negative cold bias in the Pacific Ocean. Okay. So, this is a serious issue because and it has not really changed between these two series, CMIP 3 and CMIP 5. A lot of work has been done to improve models, but this particular problem of a large negative bias over the mid latitude of the Pacific Ocean has not been solved. Now, the reasons are many. The transfer of heat from the ocean to the atmosphere is mediated by the wind speed in the atmosphere and the temperature difference between the ocean surface and the atmosphere next to it. Okay. Now, this coupling between ocean and atmosphere cannot be specified. It evolves as the model is integrated. So, all we can say is that there is some problem in these models, in all of them, not one model, that they tend to have very cold ocean temperature in the mid latitude Pacific as well as mid latitude Atlantic. Okay. In addition, you also see that along the coastline of Africa, the west coast of Africa, the west coast of South America, there is a warm bias. That is, the model predicted sea surface temperature is larger than the observed. Now, this we know why, because the model resolutions are not large enough to correctly capture the upwelling, that the upward velocity in the ocean, which brings cold water from below to the upper level, which is very critical for the climate. That is not captured in these models because the model resolution is not high enough, because this coastal upwelling occurs over a very narrow region, and in order to capture that you need a very high resolution close to the coast, and if you do not capture that you will have these warm biases. Okay. This error will be reduced as the resolution of the model keeps increasing with the computers getting better and better, but this large bias in the middle of the Pacific Ocean is a serious issue, because this cannot be blamed on resolution. Okay. Because this error is over a large region, while this warm bias is confined to very close to the coast, the cold bias is very large. Okay. So, this issue is still being research is still going on to figure out why it is happening. Now, why you have to worry about all this? Because you can see that two different models, one from Japan, MIROC, the other from USA, NCAR, they simulated the impact of doubling CO2 at the rate of 1% per year, and by 2080 the MIROC model shows a 3-degree warming, while the NCAR shows 1.5, and this difference can be clearly related to the difference in cloudiness. In the MIROC model, the cloudiness decreased by about 2%, while in the NCAR model increased. So, as you recall, even a 1% change in cloudiness has a big impact on the energy budget, because clouds reflect radiation to space. If your model predicts too high a cloud, the temperature will go down. If the model shows a decrease in cloud, temperature will go up. Okay? And this is connected to cloud radiative forcing, which we discussed earlier in the course. So, this particular slide shows clearly how sensitive our ability to predict the future warming of the global mean temperature on the correct prediction of the change in cloudiness. Now, that problem has not been solved yet, because clouds come in a variety of forms. We have discussed that before: cirrus, cumulus, shallow, deep, and so the models are not capturing these clouds accurately, because models do not predict clouds from first principles. Because the model resolution is not very high, clouds are put in empirically in these climate models, and therefore, there is a large difference between different models which use different empirical data to model clouds. Now, this can also be seen in the total cloud as observed. This is annual mean, and what is produced in CMIP 5 and a more recent model CMIP 6 compared to the observation. So, you can see that the total clouds is lesser in most of the models, is the average of many models, and this has not changed much from 5 to 6, and there is a clear problem at polar regions. The cloudiness is too high, and in the tropical region cloudiness is too low. So, this problem has not yet been solved. If you relate that to liquid water path, the total amount of liquid water from the surface to the top of the atmosphere, you see that the liquid water path is too high in CMIP 5, and it is somewhat reduced in CMIP 6, but still is positive, and liquid water path is too low in the polar regions. Okay. How about ice water path? Ice water path, both CMIP 5 and CMIP 6 show lower ice water path than the observed. Okay. So, this issue of clouds, the amount of liquid in the clouds, amount of ice is still not well simulated. Now, this has an impact on short wave cloud radiative effect and the long wave cloud radiative effect. And lastly, we see the total water vapor, which is a very important parameter for rainfall and radiation. And you can see that over oceanic region, the models have a lower water vapor than observed, okay, while over land region they are a little higher. Okay. So, this issue is to be remembered as something which is not yet completely resolved in climate models: clouds and ice water path and liquid water path. Okay. Now, here is a close up of comparison between 32 general grid models, and we are comparing only the clouds over oceans, because the oceans form 70% of the globe. We have to get everything right over ocean. You can see that on the left, observation shows that annual mean cloudiness, total cloud amount, is 71%, while the multi-model ensemble of 32 climate models shows it is 57%. Although the spatial pattern is quite good, it looks quite similar, but the total amount is wrong by 14%, which is very large, because even 1% change in cloudiness has a huge impact on our climate. Difference of 14% in the annual mean cloudiness is a very serious issue. Okay. Now, how about low cloud amount, that is cloud near the boundary layer, and there also you find that the observed low cloud amount is 49%, while the modeled cloud amount, multi-model ensemble, 32 models, there is a huge difference. Okay. You can see that in the tropics, the models have a lower cloud, the low cloud amounts are lower than observed, and so it is the case in the polar region. Both in the polar region and the tropics, low cloud amount are not correctly simulated. Okay. So, this issue, until it is resolved, we cannot be very confident about predicting regional climate. In the case of global climate, certain errors cancel out, and as you have seen, models have correctly reproduced the increase in temperature from 1850 to 2023. Okay, we saw that earlier, global mean temperature. But based on this result here, you should be concerned about the ability of the model to correctly predict sea surface temperature in certain parts of the world, because both the low cloud amount and the high cloud amount are not correctly reproduced. The high cloud amount is not bad, the spatial pattern is okay, amount is wrong. The low cloud amount is wrong in total as well as the pattern. Now, let us look at the vertical structure. Today we have satellite data using LiDAR, which is able to probe through the atmosphere using a laser, and this is what the Calypso radar shows about cloud percentage with height, global mean. Okay. From a paper by Lau et al. Published in Jan 2023, and this is the difference between CMIP5 and Calypso as well as CMIP6 and Calypso, and you can see that the models have too high a cloud fraction in the mid troposphere and too low a cloud fraction near the surface. So, this issue is clearly highlighted here in the annual mean. We are not talking about even a particular month, we are talking about annual mean. In the annual mean, the model's low cloud amount is very different from Calypso. It is much lower by as high as 20%. Okay. So, all these results have been shown to you to remind you that we need to be very cautious about models' ability to predict clouds as well as rainfall on a smaller scale. Okay. Global mean is fine, things do cancel out, but you come to local, tropical, mid latitude and polar, you need to be very careful, because models are not doing too well as regards local clouds and local rainfall. Okay. And this is another comparison between CloudSat, another satellite which had a radar, and compare with CMIP6, CMIP5 with CloudSat, and again one sees a negative bias here of cloud liquid water. This is not cloud fraction, cloud liquid water. So, the cloud liquid water in the models are lower than the observed, and it has not improved from CMIP 5 to CMIP 6. We expect some improvement as the models evolve in time, but here it has not happened. Okay. Other things have improved, but cloudiness is and cloud liquid water still is a challenge. And this cloud liquid ice, and there the models are over predicting the ice content at the mid troposphere as well as at the lower level in the mid latitude and polar regions. So, this is also an issue. Both ice cloud and water cloud are not being correctly predicted because of the way the model parameterizes clouds. It is not, clouds are not being simulated from first principles. We are using some empirical model to convert the relative humidity and other parameters which are simulated model to calculate cloud liquid water and cloud ice, and there is some lacuna in the models. To bring this out more clearly, here I am showing you the vertical variation of ice fraction as a function of temperature. Okay. Now, look at the black line, which is observation. You do expect that when you go to very low temperatures, you should have a very high ice fraction. Most of the condensation of water should go to clouds, and that what observation confirms. In the polar region, for example, you would expect very low cloud, very high ice fraction, while in the tropics, when the surface temperature between 280 and 300, you should expect very low ice fraction. Now, models correctly reproduce a low or zero ice fraction in the tropics, that is not surprising, but as you go to low temperature, the way the ice fraction increases in the observation and the way it increases in the two models, CMIP 5 and CMIP 6, are very different. The observation shows a rapid increase in ice fraction and approaching 50% by the time you get to 250 Kelvin, but the models are showing 50% only at around I would say 260 or 255. But as you go to even lower temperature, the observation shows a rapid increase in ice fraction, while the model shows a gradual increase. This is a very serious weakness in the models, that as the temperature goes below 250, the ice fraction should have rapidly increased to 100%. So, this again shows a need for further improvement in the models, the way they model ice fraction. Okay. So, these weaknesses should be remembered when you try to understand the model's prediction about the future climate. Now, the other thing very important to understand in models is the wind, because the model winds at the lower level, that is around 850 millibar, okay, determines how much stress is imposed on the ocean. Remember that ocean circulation is driven both by the changes salinity temperature in the inside the ocean, so called thermo-Haaland circulation, as well as the stress imposed by the atmosphere on the ocean. Okay. So, we want to know what the stress is, and that is defined right below here. Stress in the zonal direction, meridianal direction in terms of the wind speed W, the density of air, the drag coefficient, and the of course, the angle of the wind from the true north. Okay. Now, we can compare here, black will be treated as observation here, and the dotted line is the multi-modern mean, and you can see that the models tend to over predict the zonal wind stress both in the northern latitude as well as in southern latitude is not that bad. Northern latitude the wind stress is too high. At the equatorial region, tropical region is slightly low, but it is not too bad. So, this is critical because if the model does not impose the correct wind stress at the ocean surface, the ocean circulation will not be realistic. Okay? And we saw how important the ocean circulation is to transport heat from the tropics to the polar region. That is the only major mechanism we have in addition to the atmospheric transport, and if we do not do that correctly, the model will not correctly get the ocean circulation. On the left we have the rainfall pattern, annual mean observed is here, model is here, multi-model mean, and overall you can say it is quite good. In spite of all the errors in clouds and SST, it is good to know that in the big picture the rainfall pattern looks quite good. The intertropical convergence zone is correctly reproduced as to be north of the equator in the annual mean, and the specific the South Pacific convergence zone is correctly reproduced here. Okay. But the rainfall in the Indian Ocean, which is important for people in India, is somewhat lower than the observed. Okay. And also you can see that in the Bay of Bengal the rainfall prediction is poor. We will talk about this in more detail later, because we will talk about Indian monsoon and how well the Indian monsoon is simulated by climate models. But here you can see it is not going to be too good, because in the Bay of Bengal the model simulations are not too good. Okay. Now, how about ocean circulation, ocean temperatures, not at the surface, but deep inside. So, here we are showing you the contours, okay, or the temperatures which are contours show the time mean observed potential temperature, the temperature possible to have is taken to the surface, that is called potential temperature, and zonal average or all ocean basins, okay, that is the contour. This is the potential temperature, and the simulated minus observed difference are in color. Okay. Color show the difference between simulated and observed, and you can see the cold bias near the surface and a warm bias deep inside. Okay. This is an important problem which will have an effect on heat transport in the ocean, that the models are too warm about 1 kilometer or about 500 meters below surface and too cold at the surface. Okay. So, this is an important limitations in the climate model, that at the surface they are too cold and deep inside they are too warm. Okay. Now, the reason why models are not doing as well as in the atmosphere is, you must remember that till recently we did not have accurate data of the temperature of the ocean inside, not surface we had data from satellite, but deep inside the ocean the only way we can get temperature is sending sensors deep inside the ocean, and that is very costly and complicated. And only in the last 20 years we have floats called ergo floats which go inside the ocean and come back. We have data for the last 20 years, and before that we had almost no data. So, this large error will be corrected, I am sure, in the future models as we improve the model simulations. And what is the major reason for this large errors? One of the reasons is turbulence. In the ocean the major cause of error is the modeling of turbulence, which we have not understood well because we do not have data. Okay? How turbulence changes from the surface, where turbulence is induced by the wind acting on the surface, to deep inside, where turbulence may be governed by thermo-Halion circulation. Okay? So, this issue is still on research is going on, and one may expect some improvements in the coming years. Okay? The second thing you have to worry about when you look at models is how will they simulate the seasonal cycle of temperature. Because if a model cannot simulate the seasonal cycle, that model cannot be trusted to predict climate change in the future. Okay? Now, here we are showing the snow albedo feedback during climate change, okay, and how it is related to seasonal cycle of the snow cover. Okay. On the x axis is the seasonal cycle in the snow cover as a function of temperature in different months, and on the y axis is the change in snow albedo feedback as the warming occurs in the model. Okay. If the model's seasonal cycle change in snow cover is close to the observed, which should be around here, then you can trust the model. Now, you can see that among all the models shown here, about 23 models, I would say only 3 models have the seasonal cycle in the snow albedo change close to the observed. Some models are too high, some models are too low. Okay. So, we have a problem here because only 3 of the 23 models have a seasonal cycle which is close to the observed. So, this issue is very serious because the changes in snow and ice have an impact on albedo and they impact the global warming. Okay. So, this is again needs to be improved. Now, here is a paper by Georgi and B showing the change in rainfall during 2081 to 2100, the last 20 years of this century, compared to the last 20 years of the last century. Okay. Average over April to September, the monsoon season in the northern hemisphere. And what do we see? We see that models predict an increase in rainfall over India and China, increase over the equatorial Pacific, and decrease over the African region, Mediterranean region, South Africa, the equatorial Pacific, and parts of America. Okay. So, this prediction is very interesting because some of these regions, especially the Americas and Africa, have experienced increase in drought. Okay. So, this may indicate that the impact of climate change is already being seen in some of these regions. Okay. Now, this depends on which scenario you are simulating. Here in this paper it is A1B. A1B is this the green line, that is where the carbon dioxide concentration is increasing from 380 parts per million in 2000 to 700 parts per million, which is what is happening, the rate which is growing now. And so, this is a scenario which will happen if we do nothing about CO2 emission. Okay. If that happens, this is the prediction about 10 to 20% decline in Africa, as both North Africa and South Africa, and around 10 to 15% increase in India and China, and a decline in Central America and western part of North America. Okay. So, this is indication that global warming may be causing these changes. Now, in these models, if you want to understand how we can trust these simulations, you have to look at what is called the time of emergence, because all these models have interannual and interdecadal variation, which are a part of the natural variation of the atmosphere ocean system. Okay? So, you cannot trust that result totally unless you remove the natural variation from your simulation. So, in this paper, Georgi and B are talking about in the A1B scenario, which I showed you in the last slide, at what time the signal of the climate change due to CO2 increase emerges above the natural year-to-year and decadal variation. The numbers are all quite high. For example, take India for example. India, if you look at, only by 2050 we can be sure that the impact of CO2 increase above the natural variation can be seen. So, till about 2050 you can't be sure whether what change you are seeing is on account of CO2 increase. So, this is a problem many people do not understand. Models do predict an increase in rainfall in India, but this need not be totally trusted until 2050, because there is natural climate variation because of the exchange of heat between ocean and the atmosphere, which creates various decadal oscillation called Pacific decadal oscillation, the Antarctic multi-decadal oscillation, and the El Nino phenomenon. All these oscillations are occurring year to year and decade to decade, and your impact of CO2 increase will emerge as a signal only after about 2050 in many parts of the world. Okay? So, this must be remembered before people make dire predictions about what will happen in the next 10-20 years. We cannot do that because there is a lot of natural variation in these models. Okay? So, we will stop the lecture at this point. I will continue the discussion in the next lecture. Thank you.